Hope you're having a good Saturday, getting ready for your weekend. We're still under COVID restrictions here. Can't go anywhere. Anyway, today I want to talk about gravity. I know this is a touchy subject for flat earth people. Started to say idiots, but you all know that, I guess. Anyway, it's a touchy subject. How often, I can't even think of how often I've heard flat earthers say gravity is not a force. Einstein said gravity is not a force. Brian Cox said gravity is not a force. However, I gotta emphasize to you that gravity is a force. Maybe it's not the typical force that we see, if you're going to push a car or push a table, whatever, but it is a force. The problem, I can tell you just real quick from my point of view, the problem with astrophysicists is that gravity appears to be instantaneous, so that even far across the galaxy, the gravity between two objects seems to be instantaneous, which violates relativity. So anyway, I wanted to show you just real quick some videos where gravity is proven to be a force and proven to be part of Einstein's relativity. So here we have a video from Eric Verlinde. He's a Dutch astrophysicist, and I'll let him introduce himself on the video. So let's get started with that.
Our speaker of tonight, Eric Verlinde. Well, to you, he must be very well known, especially for his alternative theory on gravity. And he seeks to find an explanation for gravity that's consistent with both quantum mechanics and general relativity.
Here, Dr. Verlinde is explaining how Newtonian gravity works, and over he talks about the force of gravity, Newtonian gravity, whatever. So listen to this one real quick.
So let me start with Newton. Of course, you all know that the law of Newton tells us how the force between two masses acts as a function of the distance, goes like 1/r². It's the same as how the surface of a sphere would grow as a function of the distance, namely it goes like r². This actually is already a hint that gravity has something to do with this area of spheres, or something like an r². And later I'll indeed show you connections with that, for instance, with how entropy arises in black holes. It's also associated with areas. But it's basically this 1/r² law that is telling us that. So this law tells us very well how planets move in the solar system, and it has been tested very precisely. If you look at how the velocity of planets behave as a function of the distance, Newton's equations would tell you that the acceleration is v²/r is equal to gm/r², and from this I can read off that the velocity should go down as a function of the distance, and if you look at the planets, that is exactly what happens.
Okay, this is a very short clip, and he explains how Newtonian gravity relates to Einsteinian gravity, relativity, and I thought it was a really good, quick explanation. So let's hear that one.
So Einstein indeed could explain what happens to Mercury, and he could explain many more things, in particular also how light behaves in the presence of gravity.
Okay, so I've shifted to another video. This guy is doing math on a whiteboard. First of all, he shows how Newtonian gravity fits in with Einsteinian relativity, and then he takes the Einstein equations and works some math, and out pops Newtonian gravity. So you can see clearly from the equations, from the calculations, that Newtonian gravity is clearly related to Einstein, and definitely Newton and Einstein do not cancel each other out. Okay, so let's look at this one.
We've gained a little bit of familiarity with the stress energy momentum tensor. Let's return to the Einstein equation. So the Einstein tensor G mu nu equals 8 pi times Newton's constant G over c to the fourth power times the stress energy momentum tensor. Remember, G is constructed from the Riemann tensor, which in turn is constructed from the metric. It involves second derivatives of the metric tensor. So this is a set of differential equations telling us what the metric is for a given matter distribution, T mu nu. Differential equations for the gravitational field G mu nu with matter distribution defined by the stress energy momentum tensor T mu nu. The analog of the Einstein equation in Newtonian gravity is the Poisson equation. Del squared phi equals 4 pi g times mu. So here phi is the gravitational potential, del squared is just the Laplacian operator, g is Newton's constant, and mu is the mass density. My next goal in this lecture is to give you a feel for the connection between the Einstein equation and the Poisson equation of Newtonian gravity. So let me begin by reviewing Newtonian gravity. So we have a mass, say capital M, at location capital X, and that's the position vector. Here's a mass little m with position vector little x, and r vector connects these two. It's little x minus big X. And now the force that big M exerts on little m, the gravitational force, is equal to minus Newton's constant little m big M over r squared times r hat, the unit vector formed from r vector. And we can write this gravitational force in terms of a potential. So we can write F grav as minus little m times the gradient of a potential phi, where phi in this case is minus g big M over r. So these equations express the gravitational force on little m in terms of the gradient of phi, where phi is the gravitational potential at this location created by the mass big M. Now, if we have more than one mass, say we have capital M1, capital M2, etc., then we simply add the potentials. So the total potential would be minus gm1 over the distance between the mass m1 and the mass little m, so that's the magnitude of the separation vector, little x minus big X1, minus gm2 divided by little x minus big X2, and so forth. And the force on the mass little m due to all these masses is once again given by minus little m times the gradient of this potential.
So I think you can see from what I've shown you today that Newtonian gravity is important. It works. It does what it needs to do within our solar system. We have calculated the orbits of planets. We know from the math, the equations, exactly where the planets are. They can be observed. We discovered the planet Neptune using the math to predict where its orbit was. So Newtonian gravity, the force is or gravity is a force, is definitely works here on Earth and in the solar system. It's only when you get into the very heavy, very large bodies that relativity cuts in, when you're talking about the bending of light and all of those things that have to do with relativity. So that's all I had today. I hope you have a great week, and we'll see you on the next video.